objects in Self can change, and so if we want to implement TinySelf in F#, I have to tell you a little bit about working with mutable data. In F#, there's multiple different ways of representing mutable state. We're going to use records with mutable fields. So you've seen records already. Record just has a couple of properties of different types, and by default, records are immutable. You can't change them. You can only create a new value by copying the existing state and maybe changing some of them. But you can also define fields of a record as mutable, and then you can assign a new value to the field. The other option is that we could have used classes, and you can implement classes with mutable fields and mutable properties as well. Syntactically, using records will be a little easier. An interesting thing is that even if you have a mutable record, by default, they're still using structural equality. So if you compare two records, the F# system will compare their values. But this doesn't work if your records are containing something of a type that's not comparable. So in particular, if you have functions in your records, and we will have that for native functions, native methods implementations, then you can no longer compare them. And in F# you could optionally mark the record with this reference equality attribute to override that behavior. But we're not going to do that. But this means that it's not going to be easily directly possible to compare records. So what's the syntax? So to mark a field as mutable, you can use this mutable syntax. So we're defining a person who has a name and a book, and both of these are mutable properties. And one thing that I'm showing here on this slide is that it's sometimes a bit easier to define helper functions for setting the properties. So the underlying syntax that you can use is this left arrow. That's an assignment in F#, and this is setting the name of a record P to a new value n. But I can also define two helper functions, setName and setBook, that will set the value. And if I then have a record, for example, here I have a record with a name and a book, then I can call setName and setBook, and this will change the respective properties of the record. The assignment operation returns unit, and so this is an expression that returns a unit, and we can ignore whatever we get back as a result. The other thing that I'm showing you here on this in this example is one interesting aspect of pattern matching. So you can pattern match on mutable records just like you can match on immutable records. But one interesting aspect here is that you can also use this to extract some particular data value from your record. So if I want to, given the record, person, if I want to see whether they have a book, and if so, get the book, this is something where normally you would have to say match. Well, maybe we could match the x.book with an option, and that would work as well. But the interesting thing that you can do is you can pattern match on records and specify only the properties that you're interested in. And for each of the properties, you can again specify a nested pattern. And so here we're taking any person where the book matches this pattern. So there's some book, and then we get the book. And this is a useful trick. It makes extracting data from records sometimes a bit easier. So let me show you how we implement something that's a little bit like what we will need in our TinySelf. And in TinySelf, we will have an object, and the object will have a mutable list of slots. So we'll have mutable slots, and this is going to be a list of slot record, and a slot is going to be another record, and a slot will have a name of string. It will have a flag indicating whether it's a parent slot, and it's going to have contents, and that's the value of the slot, and that's again some other object. So that's why we need type and syntax here, because we're defining two mutually recursive types. Now we can define some objects. So an empty object will just have an empty list of slots. If I want to create a cat, then I can create an object where the slots will have maybe a one slot here. The name is going to be this is going to be the name of the cat, and this is not a parent slot, and the contents of this is going to be empty object. We don't have a way of representing strings in this demo, so I will just put in an empty object, and then if I define my types and evaluate these objects, then I get back my cat object. And I can mutate this. I can mutate the slots, and I can say, well, let's make this empty. So cat now has one slot. If I mutate this and run the mutation and then look at my cat again, now it has no slots in it. So we've removed the name. So to make changing the slots a little bit easier, I can define some helpers, and I'm going to define a helper called addSlot, and this is going to be taking a name and the contents and the object that we want to modify. And what we're going to do is we're going to define a new slot, and addSlot is not going to create a parent slot. addParentSlot is going to create a slot that is a parent slot. So here we just say name is this N, contents is this C, is parent is false, and now we're going to mutate our list and set it to a new list with this extra slot. And addParentSlot will be similar, but it will set parent to true. Now, if we want to create something like our earlier cat example, then I could create a Cheshire cat by creating an object that's initially empty, and then I can call all the different operations on it. And the syntax will be slightly nicer if we use the pipe operator, because we always kept the object that's to be modified as the last argument. And so I can say Cheshire addSlot name, and this would be the string value. And now I can also add the parent slot to it, parent, and this we're going to set to some cat object, which I'm going to just keep empty for now. And so if I now create my Cheshire object at the start, this has no slots. Now we added a name and the value is now with one slot. Now we add the parent, and if we run it again, now there's two slots. So to illustrate the interesting features of pattern matching that I was showing earlier, what we can do is we can try to find all the parent slots in our objects. So if I take Cheshire and access the slots and filter it to only find the parent slots, then this gives me, we can see, and if we run it, just one slot. But we can call this parent slots, and then if I wanted to check whether there's just one parent slot, then I could say pattern match on this list with one record inside, and maybe we can get the name of this and the contents, but we're ignoring the is parent property because we know that has to be true, and then we can say one parent and maybe print the name of the parent. Otherwise we'll say 0 or more than 1. And so if I run the pattern matching, then right here we can see there's just one parent called parent star. So that's enough of F# that you will now need in the TinySelf implementation. But there's more interesting and more fundamental thing, which is that the code we will be writing for TinySelf is going to be using a fundamentally different programming style than from what we've seen before. Before, we always had nice algebraic data types to represent our expressions with all the different cases. Then we had dictionaries to store our variables. But in TinySelf, pretty much everything is going to be an object. And the type definition in all the earlier labs, all the earlier Tiny systems, we were changing the type definitions as we were adding new features. This time, the type definition will stay the same throughout the whole development. This uniformity, of course, has drawbacks. In particular, it means that everything will type check. If you put a wrong thing in your object, it will still compile and you will be able to run your code, but you will get some strange runtime error later on because you are expecting an object of a different kind, containing different things. To help with debugging this, the TinySelf demo, the TinySelf task comes with a little object visualizer that you can load and use to see what your objects look like. So I have some example from the lab here, and this is creating an object called Hello World and Hello Mudface. They both have a parent slot called greeter, which then has a greeting and a greet method, and they have a slot called who. And if I load the visualizer and print the object tree, then what the visualizer does is that it creates a little box for each object that we have in the world. So if we visualize just this one, then this is an object where it has who. This then is a string value matface. There's a greeter object. That's this one. This has greeting and a greet method. Greeting is a string value called number 8. That's hello. And greet is number 7. And that's some sort of native method here. So with this, you can always get a somewhat readable visual representation of what your objects look like. And another thing that you already saw in the code is that we will simplify the object construction by creating a bunch of helper methods, because constructing all these records with nested lists in them syntactically is a little challenging, and we're going to make that easier by defining all these make helper functions that will create the right kind of data structures and the right kind of objects. So here, each of these make functions that are in the code sample is actually creating just a new object. But if you put them together like this, then you're creating a data object with parent slot, normal slot, and an assignment slot. And this way, your code will become a bit more readable and understandable.